Hello, the next lab that we are going to work on is called the water lab. I'm going to provide you some information for the water lab in order for you to complete the water lab. First, we have to talk about some basic concepts so that you understand the water lab. So, I'm going to go over some terms. The first term here is going to be matter. Matter is going to be anything that takes up space and has a mass. Anything that takes up space and has mass. And you can think of mass as weight just for now. So, really, anything that takes up space. Let's think about examples of things that take up space. The pen takes up space. This piece of paper takes up space. You take up space. I take up space. Plants, animals take up space. Even bacteria take up space. Even things that we cannot see, such as oxygen gas molecules that you are breathing in and carbon dioxide gas molecules that you are breathing out, takes up space and has a mass. So everything that is made of matter is basically made from the elements from the periodic table of elements. If you do not know what a periodic table of elements looks like, then please check out our free online textbook, Chapter 2. So I'll put that next to it because the topics for the water lab are included in Chapter 2. Matter is made of the elements from the periodic table of elements. All matter is made of elements. Can you think of some examples of elements? I hope you are thinking of a few types of elements, such as oxygen, hydrogen, helium, sodium, chlorine, carbon. The elements from the periodic table of elements are usually abbreviated by one or two letters. For example, hydrogen is abbreviated with the letter H in the periodic table of elements. Oxygen is abbreviated with the letter O in the periodic table of elements. Nitrogen is abbreviated with the letter N in the periodic table of elements. And carbon is abbreviated with the letter C in the periodic table of elements. Some other elements that are important will be sodium. The abbreviation for sodium is Na. Another element that is important is chlorine. The abbreviation for chlorine is Cl. We have many elements from the periodic table of elements, and since we are in biology, we are really focused on the elements that are found in living organisms. For example, what elements make up us, human beings? What elements make up bacterial cells? And what elements make up plants and other animals? So, not all elements from the periodic table of elements make up living organisms. So, when we talk about elements from the periodic table of elements, we are going to be talking about the elements that are found in living organisms. Most of the elements found in living organisms are found within the first 3 or 4 rows of the periodic table of elements. Some elements are found in living things in a great abundance. We call those elements major elements. Some elements are found in smaller amounts. We call those minor elements. And some elements are found in really small, minute amounts, and we call those elements trace elements. Let's give an example of some chemicals, which we're going to call molecules, that are good examples of matter for this class. 1. Water. Water takes up space and has a mass. The formula for a molecule of water is H2O. Let's talk about another one. Oxygen gas that you are breathing in right now. The molecular formula for oxygen gas is O2. We're going to talk about two more examples of chemicals. Carbon dioxide gas is the third one. And the molecular formula for carbon dioxide gas is CO2. How about this one? Glucose, which is an example of a sugar. This is a chemical or a substance that we talk about frequently in this class. Does anyone know what the molecular formula for glucose is? It is going to be C6H12O6. So this one is a very large molecule, and we tend to call large molecules macromolecules. So that term macro means big, a big molecule. When we talk about elements and matter, we definitely have to talk about this term called atoms. In order to understand what an atom is, we have to refer back to the periodic table of elements. We have over 100 different types of element in the periodic table of elements. Each element is very unique, just like all of us in this class are all unique and have our own set of characteristics that makes us different from each other. Elements in the periodic table also have characteristics that make them different from other elements. So an atom is the smallest part of an element that will demonstrate the unique characteristics that the element has. Smallest unit of an element that demonstrates the element's unique characteristics. So what are some examples of the unique characteristics that elements have? Well, elements have different sizes. They also have different masses, which means they weigh differently from each other. Those are two examples of unique characteristics demonstrated by different elements. An atom also has another meaning. An atom will allow us to understand how much of an element that we have in a substance. For example, if we go back up to water from question number 1, okay, we can basically see how much hydrogen we have in water. We have 2 atoms of hydrogen and 1 atom of oxygen. The 1 goes without saying, so basically you're never going to see a 1 next to an element. For example, water, which is H2O, doesn't have the 1 next to it. I was just using that for purposes of teaching. So therefore, the atom allows us to understand how much of an element that we have in a substance. For example, how many of atoms do we have in carbon dioxide? We have one atom of carbon dioxide and a molecule of carbon dioxide gas, and we have two atoms of oxygen and a molecule of carbon dioxide gas. So therefore, we're going to add on to our definition of atom. We will add on that atoms allow us to quantify how much of an element is in a chemical or a molecule. So now let's talk about the structure of the atom. An atom consists of a variety of very small substances that we call particles. The major particles making up the atoms are protons, neutrons, and electrons. It is important for you to understand that you may not find all of those particles in an atom of an element, but in most cases, you will find those three types of particles in an atom of an element. So there is an inner core of the atom called the atomic nucleus. That is the inner core of the atom. So neutrons and protons are going to be located in the atomic nucleus, which is the inner core of the atom. Proton is a particle that has a positive charge, and a neutron is a particle that has no charge. This is why it's called neutron, because it's a neutrally charged particle. Our electrons are going to be negatively charged particles. So all of these are different types of particles. And the location for the electron particles are going to be circulating around the atomic nucleus. So we will say that the electron particles are located in the orbital shells surrounding the nucleus. Let me give you an example of an atom off to the side. Okay, I'm going to draw an example of an atom of helium. The abbreviation for helium is going to be He. The helium atom contains two protons, two neutrons, and two electrons. We are going to place the protons and the neutrons in the atomic nucleus, which is the inner core of the atom. And then we are going to draw an orbital shell around the inner nucleus and draw our electrons. We will use dots to represent the electrons. The electrons are orbiting at nearly the speed of light around the atomic nucleus. And they usually travel in pairs if pairs of electrons are available. On the bottom of the page, we are going to give more examples of atoms. Let's go ahead and make some more diagrams of atoms. We will start with a hydrogen atom, which is abbreviated H. The hydrogen atom has 2 protons. I'm sorry, that's 1 proton. I made a mistake. It is 1 proton particle, and it actually has 0 neutron particles. Well, at least most atoms have 0 neutron particles, and 1 electron particle. I would like you to make sure that you understand the charge of the particle. So under each of the proton, well, there's a 0 neutrons here, and the electron, please list the charge of the particle. Remember that protons are positive, neutrons have no charge, and electrons are negative. When the number of positives and the number of negative particles are the same as each other in an atom, we say that the atom is electrically neutral because they basically cancel each other's charge out. So if we have 1 positive particle and 1 negative particle, we call that atom electrically neutral because those particles essentially cancel each other's charge. So first we're going to draw the inner core of the atom. We'll go ahead and list that there's 1 proton particle. There's 0 neutrons in there. And we're going to call this the atomic nucleus, which is the inner core of the atom. Next, we're going to draw a ring around the atomic nucleus. This is what we call the electron orbital shell. And it looks like hydrogen only has 1 electron. So I'll place that electron in the electron orbital shell. Let's do another example. Let's draw a carbon atom. Does anybody know the abbreviation for carbon? It is going to be C. I'm going to list the number of proton, neutron, and electron particles that make up the carbon atom. It's going to be 6 protons, 6 neutrons, and 6 electrons. The first thing that we're going to do is we're going to draw that inner core of the atom called the atomic nucleus. And it's going to have 6 protons and 6 neutrons, as we see right here. The next thing we'll do is we will draw a ring around the atomic nucleus, and that's going to be the electron orbital shell. Well, it turns out that the first electron orbital shell can only hold a total of 2 electrons. So that is its maximum capacity. So we have a little problem here because carbon has 6 electrons. We're going to draw 2 electrons in the electron orbital shell, but now we have 4 more electrons. We're going to have to draw another electron orbital shell in order to fit those electrons. So we drew 2 electrons already, and now we're going to have to put the remaining 4 electrons in the second electron orbital shell. So carbon is a little bit different than hydrogen because carbon has 2 electron orbital shells. So we want to make sure we know that the second electron orbital shell can hold 8 electrons. 8. That means that this electron shell is not full. The second electron orbital shell is not full. The outermost shell of an atom is called the valence shell. So the valence shell, if we refer back to the hydrogen atom right here, the valence shell only has 1 electron. I know there's only 1 electron orbital shell, but since that is the only electron orbital shell, we're going to call that the valence shell. That would be considered the outermost shell. The carbon atom has 2 electron orbital shells. What we're really looking at is the outermost shell. Okay, so the outermost shell for the carbon atom is not full to capacity because remember that the second shell can hold up to 8 electrons. So how many openings do we have in carbon's valence shell? Well, it looks like we have 1, 2, 3, 4 openings. So there are 4 openings in carbon's valence shell. Why is that? Because the second orbital shell can hold a total of 8 electrons, but there is only 4 electrons, as we see drawn right here. Anytime that an atom has a valence shell with openings, then that means that atom is going to be reactive. So let me ask you for practice, are there any openings in hydrogen's valence shell? And the answer is yes, there is 1 opening. So therefore, the hydrogen atom is reactive. But if we look back to our helium atom on up here on our page, we see that the outermost shell, which there's only 1 shell, but the outermost valence shell has 2 electrons and it is full to capacity. And that means that the helium atom is going to not be reactive. So this helium atom is not reactive. In biology, we are going to be interested in reactive atoms. The reason that we are interested in reactive atoms is because the reactive atoms react with each other and form molecules that we need for life. Examples are water molecules, oxygen gas molecules, carbon dioxide gas molecules, and glucose sugar molecules, as well as larger molecules such as proteins, carbohydrates, fats, and DNA. We have to go on to our next topic, which is going to be ions. Move it down. An ion is an atom that has lost or gained an electron an atom that has lost or gained an electron. So I want you to recall, we just talked about diagrams of atoms, and we talked about how electrons are found in the outermost shell. We also talked about how when electron orbital shell or the valence shells are not completely full, that the atom is going to be reactive. Reactive atoms, again, are important to us because they make up the molecules of life, such as water, oxygen, carbon dioxide, sugars, DNA, proteins, and many more. When atoms react, they tend to either lose electrons, gain electrons, or share electrons. Anytime atoms lose, gain, or share electrons, bonds are normally formed. Chemical bonds are found within molecules that are important for life, such as water, oxygen, carbon dioxide, sugar, DNA, proteins, and so on. Let's give an example of two atoms and show these atoms losing and gaining electrons, or what I like to call a transfer of electrons. In order to show how an ion is formed, I will need to draw two more atoms. I am going to draw on the left side under question number 3, a sodium atom. Does anyone know what the elemental abbreviation for sodium is? Na, which stands for natrium. It is Latin. And next to the sodium atom, I'm leaving a space open because I'm going to draw a chlorine atom. Let's start with the sodium atom. The sodium atom has 11 protons, 12 neutrons, and 11 electrons. So 11 protons, 12 neutrons, and 11 electrons. So the first thing that we're going to draw on our atom is our atomic nucleus. And we're going to list 11 protons and 12 neutrons inside of our atomic nucleus. After that, we're going to draw our first electron orbital shell, which contains 2 electrons. But remember right here, there are 11 electrons, which means we have 9 more electrons to go. Our next or our second electron orbital shell, which is surrounding the first electron orbital shell, will be filled up to capacity with 8 electrons. So how many electrons do we have total in our drawing at this point? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We still do not have 11 electrons, but the second electron orbital shell can only hold 8. It turns out if the second shell is full, we can draw a third electron orbital shell, and that third electron orbital shell can also hold a total of 8 electrons. But we only have 1 more electron left in our sodium atom. Let me ask you a couple of review questions at this point. How many electrons are in sodium's valence shell? So remember, the outermost shell is called the valence shell. Is the valence shell full or not? It looks like there's only 1 electron in sodium's valence shell, so the valence shell is not full. How many openings does it have? It has 7 openings, since the valence shell can hold up to 8 electrons. Now let's go ahead and draw an atom next to that called a chlorine atom. And that abbreviation is Cl. Chlorine atoms have 17 protons, 18 neutrons, and 17 electrons. So we have a lot to draw in our diagram. We are going to start with the inner core, called the atomic nucleus. We will list 17 protons and 18 neutrons, okay, in the atomic nucleus. Now you should pause the video for just a few moments and draw the rest of the electron orbital shells to see if you can determine how the electrons are distributed. The first electron orbital shell is going to have 2 electrons. So we have filled up the first shell, but we still have 15 more electrons. The second electron orbital shell is going to have 8 electrons. We're going to fill up the second electron orbital shell. And now we have a total of 10 electrons, but we still have 7 more electrons to draw. So we have to draw a third electron orbital shell. And how many electrons are going to be found in the third shell? 7 electrons. So how many openings does chlorine have in its valence shell? The valence shell has 1 opening. This seems to be a perfect combination for the sodium atom right here, which only has 1 electron in its valence shell. So what tends to happen is that sodium will give up or lose this electron and chlorine will gain the electron. So we have an electron transfer. So when sodium gains that electron, then its valence shell is full. The goal of all atoms is to undergo reactions until their valence shell is full. When the valence shell is full, the atom is stable. So when sodium loses this electron, it now is left with a valence shell that contains 8 electrons. So its valence shell is full. So basically, when a sodium atom and a chlorine atom react, we have an electron being transferred from one atom to the next atom. It's important to note here that sodium has lost an electron, so now it has 10 electrons, and chlorine has gained an electron, so now it has 18 electrons. This atom is no longer electrically neutral. Remember that proteins are positively charged particles, and electrons are negatively charged particles. So now sodium has 11 positives and 10 negatives. So this is when we write sodium like this. Here's Na, the symbol for sodium, with a little plus sign to the upper right or superscripted. This plus sign indicates, if we look back up here to the definition of an atom, that this atom has lost an electron. Now the atom is charged. And it's positively charged. So anytime you see an element such as this sodium atom right here with a little positive or another element with a little negative sign, then you should recognize that as an ion or an ionic substance. So over here, Chlorine has 17 protons. The number of protons did not change. We have 17 positively charged particles. But now, since chlorine gained an electron, we have 18 negatively charged particles. So our chlorine gained one electron, which is negatively charged. So we put a negative sign by our chlorine. So again, this would be our sodium ion, and this would be our chlorine ion. So you maybe have heard of an old saying, opposites attract. Well, the sodium ion will definitely attract the chlorine ion because sodium is positive and chlorine is negative. And the force of attraction that is going to connect them together is called a bond. In this case, because you have two ions, we're going to call that an ionic bond. So I want you to remember that an ionic bond is going to ultimately be formed due to an electron transfer. Okay, so let's go ahead and move on to our next topic and draw a water molecule. We are talking about the water lab. So now we're at the point where we have to basically dip into or dive deeper into some characteristics of water. So I'm on question number 4. And I just want to give myself plenty of room. So the first thing we have to do in question 4 is make a drawing of a water molecule using the molecular formula. So what is the molecular formula of water? H2O. How many atoms of hydrogen are in a molecule of water? 2. And how many atoms of oxygen are in a molecule of water? 1. So water molecule has this shape. There's our 1 oxygen and our 2 hydrogen atoms. So it turns out that a water molecule has some special characteristics. The oxygen is what we call partially negative, partially negatively charged. So let me put a little negative charge by my oxygen. But that term partially means it basically is not a whole charge. It's a slight or partial negative charge. And there is a little symbol, okay, that designates partially. This is a delta symbol from Greek symbols. So I'm going to go ahead and I'm going to put that delta symbol. And if I put that delta symbol next to a little negative, then I'm basically saying this oxygen atom is partially charged. And the reason, or partially negatively charged, the reason oxygen is partially negatively charged is because oxygen is very electronegative. It loves electrons and will pull those negative electrons towards it. Our hydrogen atoms are partially positive charged. So I'm going to put some little plus signs, and I also have to add my Greek symbol, which is delta, which indicates it's a partial charge. It's not a whole charge, like in our previous example that we gave with sodium and chlorine, which completely lost and gained an electron, resulting in whole charges. These are partially charged. That's basically saying that the oxygen atom within a molecule of water is slightly more negative compared to the hydrogen atoms. And anytime you have that difference in charge, we call that polarity. And the type of bond that is formed is going to be called a polar covalent bond. The term covalent, co usually means sharing. Think about co-ed. Polar covalent bond is going to be formed when atoms share electrons. And this is to satisfy the valence. Oh, let's cross that term out. Share electrons, but not equally. So let's go ahead and use a highlighter and highlight the polar covalent bonds, which are indicated by a solid line. So the polar covalent bonds are between the oxygen and the hydrogens within the water molecule. And a polar covalent bond is a bond that occurs when atoms share electrons, but they do not share electrons equally. So they're kind of playing a tug of war with electrons, and oxygen is kind of winning, but not totally. I want you to keep in mind that a bond is a force of attraction between two atoms that keep them connected together to form substances or molecules. Let's go ahead and draw near the bottom of our sheet two molecules of water. So let's start off with one molecule of water. I'm going to draw the water molecule out. And anytime you are showing the bonds in a molecule, that is going to be called the structural formula of that molecule. And since I'm showing you in this example of my water molecule that I drew where the bonds are located, we have a polar covalent bond here, we have another polar covalent bond here, then we would call that the structural formula for that water molecule. So the structural formula of a molecule provides a little bit more detail about the molecule because it shows where the bonds are located between the atoms within the substance. So what sort of charge does the oxygen have in a water molecule? Remember, it has that slightly negative charge, and the hydrogens have that slightly positive charge. So that means one water molecule will be really attracted to another water molecule. The hydrogen, which is slightly positive, will be very attracted to the oxygen of a different water molecule because of the difference of charge there. Even if it is only a partial charge, there is still opposites attracting. And we call that type of bond, that bond is indicated by a dotted or dashed line. That bond is called a hydrogen bond. So a hydrogen bond is going to be formed between water molecules, and a polar covalent bond, is demonstrated up here with the solid lines, are going to be formed within one water molecule. A hydrogen bond is a very weak bond that is going to be formed between partially charged substances. The overall message behind this is that you understand the terms polarity and covalent bonds, such as polar covalent bonds. So, anytime you think of polarity, you always think of something charged, positives or negatives. Let's move on to our next topic. Oh, no, we are continuing on number 4. We are talking about water in a little bit more detail. Get ready. So water has a whole bunch of special characteristics that makes it unique and important to life. So for example, water is so important to life that we search for water on other planets because we think without water, there could be no life on another planet. Water is involved in so many things that allow living, life to be sustained. One major special characteristic or special property of water is that water acts as a solvent. A solvent is basically a substance that has dissolving power. So, for example, if you have a cube of sugar or a cube of salt and you threw it in a cup of water and you stirred it up, basically the salt or the sugar will dissolve because water has that special property. It is capable of dissolving other substances. So let's talk about the types of substances that water can dissolve first. So water can dissolve something called hydrophilic substances. These are water loving substances. I'll draw a little heart right here. These are substances, if you add them to a cup of water and you mix them up, you wouldn't see them anymore. So, what are some examples of hydrophilic substances? Salt and sugar. Those are the ones we want to know at this point. As it turns out, polar substances are going to be attracted to other polar substances. That means both salt and sugar are what we call polar substances. Like ends up dissolving in like, meaning salt is polar, so it will dissolve in water, which is also polar. If a substance is able to dissolve in water, we call that a water soluble substance. We also have some substances that do not dissolve easily in water, and we're going to call them hydrophobic. They do not love water and they are not attracted to water. So I want you to think of a substance that you added to a measuring cup of water, or you just had a cup of water and you stirred it up and you let it sit on your countertop, and these two substances separated out from each other when you let it sit. Hopefully, you're thinking of vegetable oil. Oily and fatty substances are not attracted to water. They do not dissolve in water. So let's list oils, fats, and waxes. Make sure you know all this stuff for the lab, are examples of hydrophobic substances. They are not polar. These substances are called nonpolar. That means not charged. There are no positives and negatives on oils, fats, and waxes. Therefore, water doesn't know what to do with it. Water has positives and negatives built into the molecule. So it's not going to be attracted to a substance like an oily or fatty substances that have no positives and negatives. Nonpolar substances, basically what you want to know about nonpolar substances will be oils, fats, and waxes. Okay. I will stop with number 4. Oh, I'm sorry. Hydrophobic substances are not water soluble. I just wanted to add that note. Okay, let's move on to question number 5. Question number 5 is the last part of your lab. So it is going to correlate with the last part of your lab, which has to do with pH. pH is, let's add this in, the measure of the concentration of hydrogen ions. And remember, an ion is a substance that has a positive charge up there. So if I put H, H stands for hydrogen, and I put a little plus sign, kind of superscripted next to the H, that is a hydrogen ion. When substances like the hydrogen ions have positive and negative charges, they tend to react with other substances. So, therefore, if you have too many of these hydrogen ions floating around in your body fluids, it may end up reacting with other molecules like DNA and proteins and start damaging those molecules. It is important to have a balance of hydrogen ions in fluids. We use the pH scale to measure the amount or concentration of hydrogen ions in fluids. The pH scale ranges from 0 to 14. So take a minute and please write this down. A pH value less than 7 is going to be acidic. A pH value greater than 7 is going to be something that we call basic or alkaline. At a pH value exactly equal to 7.000 is what we call a neutral substance. Okay. The pH scale again ranges from 0 to 14, and you should be able to understand questions like this. Mystery substance has a pH value of 5. Is this substance acidic, basic, or neutral? That would be acidic because the pH value is less than 7. Another example would be mystery substance has a pH value equal to 10. Would that be an example of an acidic, basic, or neutral substance? Again, pH values greater than 7 are going to be what we call basic. Okay, let's go ahead and note under our pH value less than 7 for acidic substances that acidic substances have a high concentration of hydrogen ions. So they are going to have a lot of hydrogen ions. Any sort of solution or substance that has a very high amount or concentration of hydrogen ions will be considered an acidic substance. Basic substances have a low concentration of hydrogen ions. So they do not have very many hydrogen ions at all. Okay, our next topic is how do we read a pH scale? Okay, so in order to do that, I'm going to draw a pH scale across my sheet of paper. And in the middle of the pH scale, I'm going to put 7 because 7 is neutral. Do 8, 9, 10, 11, 12, 13, and this will be 14. 6, 5, 4, 3, 2, 1, and then this will be 0 right here. Okay. Let's go ahead and look at the pH value of blood. I'm going to draw an arrow on the pH scale that I drew on our notes where the pH of blood falls onto the scale. So as you can see, it is between 7 and 8. It looks like the pH of blood is approximately 7.5. So would you consider blood acidic, basic, or neutral? Blood is actually considered basic, but we call it slightly basic because it's close to neutral. We want to make sure blood stays close to that value of pH 7.5, which is actually pH 7.35 to 7.45. It has a very narrow range where blood is healthy and functioning correctly. If we move out of that very narrow range of where we want blood to be, 7.35 to 7.45 is the range of blood. That's what pH value we want our blood to read. If you move out of that range and the pH value gets higher or lower, then you are going to disrupt the functioning of blood, which is to carry oxygen. Certain diseases, like respiratory diseases and kidney diseases, may end up affecting the pH value of blood. And this tends to result in individuals with respiratory or kidney diseases to feel fatigued and very tired because blood carries oxygen to your organs and your cells, and oxygen allows for energy to be released within your cells and spread throughout your body. Let's look at another example of how to read the pH scale. Let's say normal rain, we're just adding some information here. Normal rain is a pH value of 6. Normal rain, pH equal to 6. And then let's list the pH value of acid rain, which has been recorded right here in the United States. It looks like it's a pH value of 2. So acid rain, pH equals 2. We're going to use this example in order to understand the pH scale and how we understand how acidity changes when we move from one value on the pH scale to the next value. Okay, so it turns out, and please mark this down, that when you move on the pH scale from one value to the next, you move or you increase or decrease acidity by 10 times. Okay, so if you move from a pH value of 6 to a pH value of 5, that means your new substance, which is a pH value of 5, is 10 times more acidic. And if you move from 5 to 4, it's going to be 100 times more acidic. You just keep adding zeros at each value, 1,000 times more acidic, and then finally 10,000 times more acidic. So our acid rain is 10,000 times more acidic than we want it to be, than normal rain. This is not good for us because this ends up destroying vegetation, and even historical monuments have been destroyed. Where does this acid rain come from? Well, it definitely comes from pollution that we pump up to the air. Have you ever heard of that saying, what goes up must come down? That is what is happening here with our acid rain. Pumping pollution up, acid rain is falling down. Okay, we are almost there. We're almost there. Our last page of notes is going to be talking in a little bit more detail about what an acid and a base is going to be, and I will provide some examples. So an acid is going to be a substance that increases the concentration of hydrogen ions in a solution. These brackets mean concentration. An example of a very strong acid is hydrochloric acid. Hydrochloric acid. The formula for hydrochloric acid is HCl. This over. Let's go ahead and take some hydrochloric acid. So we'll say concentrated hydrochloric acid, and let's add it to a beaker of water. So now I am now making a very basic drawing of a beaker, and I am definitely no artist. I'm going to have water in the beaker because you should always add acid to water. And I'm going to add some concentrated hydrochloric acid into the water. What's going to happen is that hydrochloric acid will break apart, or what we call dissociate, into individual hydrogen ions. And there will also be some chloride ions. So notice that hydrochloric acid broke apart. The hydrogen separated from the chloride ions. So therefore, I have increased the concentration of hydrogen ions in this solution, and that is what the definition of an acid is. Okay, I want you to realize, or I want to introduce a couple of more terms. Unfortunately, I'm so sorry, but water is always called the solvent in biology. So our solvent, I'm going to do a very basic math equation right here, an addition problem. Solvent, which in biology is always water. And I'm going to add it with a substance that I'm going to call a solute. Solute is going to be whatever you're adding to water. In this case, it's hydrochloric acid. And when you mix them together, you make something called a solution. And we're going to name our solution. We're going to call our example solution an acid solution, since we added hydrochloric acid to water. You can also make salt solutions and sugar solutions. If you add salt to water, then you will make a salt solution, and salt is going to be the solute. If you add sugar to water, then you will make a sugar solution, and the solute is the sugar. So notice that the solvent is always water, but the solute can change based on whatever you add to water. Let's keep this simple. A base is any substance that decreases the concentration of hydrogen ions in a solution. Let's call bases are going to be sponges for hydrogen ions. They will soak up all of the extra hydrogen ions, therefore decreasing the hydrogen ions in a solution. The example that we want to give for that is going to be a substance called sodium hydroxide, which is a very strong base, and it's abbreviated NaOH. The Na stands for sodium, and the OA stands for hydroxide. Just like acids do, the sodium hydroxide will dissociate or break apart into sodium and hydroxide ions when you add sodium hydroxide to water. So if we have some hydroxide ions, which are negatively charged, floating around, so here's hydroxide, and we also have some hydrogen ions floating in the water. What's going to happen is a reaction. Since hydroxide is negatively charged and hydrogen is positively charged, they will be very attracted to each other, and they will form a reaction that is going to end up producing water. So therefore, we have taken the free hydrogen ions out of the solution, which is the definition of what a base does. A base decreases the hydrogen ions in solution. Let's go ahead and note another chemical called a buffer. A buffer is a substance that prevents major changes in pH values within your body fluids, such as in your blood and other fluids in your body. Okay, please look in chapter 2 and read about substances called buffers.